Hey, so what's up everyone? I hope you are doing great. So welcome back to another video. In today's video, we'll discuss about principal component analysis, another useful and important topic. If you recall, we talked about this in regression when we were discussing about variable selection. So PCA is a dimension reduction technique. In this video, we'll see what PCA is, then what are the goals of dimension reduction, then what are the steps involved in PCA so that we can understand what is happening behind the scene, and then few terms like loadings, scores, etc. And finally, we'll do one assignment in R to see how PCA can be done. Okay, so let's jump straight into the topic and see what is PCA. Now let's say we are working on a model to classify our customers for loans. So our response variable shall have two categories, defaulters and non-defaulters. Now let's say we have predictors as gender, income, location, whether customer has a house or not, their food habits, and so on up to m variables. Now it's apparent to us that food habit has got no relation with a customer being a defaulter or not. So one way is that we eliminate this variable altogether. This is called as feature elimination. But the real life scenario is not that simple. First of all, there would be so many variables and we can't just draw a line saying that these are useful variable and these are not. Because we don't do this based on our whims and fancies. Secondly, by doing this, we are potentially losing information. We never know how a particular variable will interact with other variables and what will be its impact. So instead of eliminating the features, we use PCA. So what we do is, we don't remove the feature completely, rather we extract the features. What does it mean? It means that we use all the features and make linear combinations of it to create new variables. Now what do I mean by linear combination? Basically we create new variables that are called principal components, such that each of these variables are a linear combination of all the original variables, like so. Now you can see here, each variable is contributing to all the principal components. So we are not eliminating any variable. Instead, we have extracted information from each of the variable and captured it in principal components. This is known as linear combination of the original variable. Now these variables are ordered based on their importance. Now what I mean by importance is that these variables are ordered such that principal component 1 will explain our response variable the most. Then principal component 2 will explain after PC1 and so on. So based on how well they explain our response variable or based on the variability captured, they are ordered. After that, we can use some cutoff and select the number of features that are required for us. This way we have reduced the number of features and yet have retained maximum information from all the original variables. So isn't it a wise approach? I'm sure you would agree that this is a better approach than eliminating the features. Now let's see what is the definition of PCA. As I said earlier, PCA is a dimension reduction technique. A principal component is an orthogonal linear combination of the original predictors. And principal components are orthogonal to each other. It means that they are independent of each other or they are perpendicular to each other. Now as you can see in the left panel, we have our original dataset. And then on the right hand panel, we have our principal components. What we are doing here is that we are projecting our original dataset on principal component space. And the transformed data is called principal components, which is orthogonal to each other. Now this is an example of two variable case. We can extend this to n component space, but obviously we can't show it in the form of a graph beyond 3D. So I hope you have got the idea what is happening here. Now just to summarize, principal component analysis is a dimension reduction technique, and principal components are a linear combination of the original variables which are ordered based on the percent of variability explained, or how well they explain the response variable. And then to create principal components, we project the original data into the principal component space, which in turn gives us the principal components, which are orthogonal to each other, as shown here in the left and right hand panels. So I hope this clarifies what principal component is. So moving forward now, let's see what are the goals of dimension reduction. Basically, we achieve three goals via PCA. The first goal is, by reducing dimension, it becomes computationally effective. Then the second goal is, it prevents overfitting. And the third goal is, it reduces multicollinearity as PCs are independent of each other. So these are the three goals that are achieved through principal component analysis. Now let's see what are the steps involved in PCA. But before that, we need to go back to our basic maths. We will see what is eigenvectors and eigenvalues, that is at the core of PCA. So let's understand what are these. Eigenvector is a vector whose direction remains unchanged when a linear transformation is done. So for a square matrix A, an eigenvector and eigenvalue make the equation shown here as true. A here is a square matrix. Now what is a square matrix? A matrix with equal number of rows and columns is a square matrix. So if this equation holds true, then V and lambda are eigenvector and eigenvalues respectively. But the question is, why do we use eigenvectors? So as we know that matrices are used to store large information, but it could be computationally slow. So what we do is we multiply eigenvectors with matrix such that it satisfies the above equation. Now multiplying the vector with a matrix results in a vector that approximates the matrix. So the idea of eigenvector here is that we get a vector which is computationally efficient than a matrix, and we also are able to approximate the whole matrix. Now eigenvalues is the scale of the stretch. So 1 means no change, 2 means doubling in length, and -1 means pointing backwards. So here you can look at the picture. We perform a linear transformation, and now you may think of eigenvalues as the stretching, compressing an XY line chart without changing their direction. Also we can see here that eigenvector is a vector that does not change direction in a transformation. So I hope with this you have got some clarity about eigenvector and eigenvalues. Now we will not be calculating it manually, but as I said earlier, it is at the core of PCA. Hence it was important that we revisit our elementary mathematics and just refresh our memory about eigenvector and eigenvalues. Now let's see what are the steps involved in PCA. So the first step in PCA is to take the matrix of the independent variable x and standardize the data into Z matrix. Then take the matrix Z and transpose it and then multiply it by Z. This Z transpose multiplied by Z will give us the covariance matrix of Z. Now calculate the n orthonormalized, that is perpendicular, eigenvectors and their corresponding eigenvalues of Z transpose multiplied by Z matrix, which is basically the covariance matrix, and name them as V1, V2, V3 up to Vn. And in the same way, name their corresponding eigenvalues as lambda 1, lambda 2 up to lambda n. Now V1, V2 up to Vn are called as principal components. And these vectors of eigenvectors is sorted from highest to lowest, and hence we can name it as V star. Now in the next step, we calculate Z star as Z into V star. Now this new matrix Z star is a standardized version of X, but now each observation is a combination of the original variables, where the weights are determined by the eigenvectors. and each column of Z star is independent of one another. Then finally we will decide how many features to keep and how many to drop. Now to decide this, there are basically three methods. We can either decide based on the requirement, say we need our results in 2D, hence we'll only keep 2 PCs. Or we can decide based on the total target variation of PCs, say 80% is our target variation. So add proportion of variation explained by PC1, PC2, PC3 up to PCN, and when 80% is reached, then stop and select those number of principal components. Or calculate the cumulative proportion of variance explained by each feature and then plot a scree plot and select where elbow forms. So this is how you can select number of principal components. Now let's see few important terms that you will come across in PCA, which are loadings and scores. First we'll see what loading is. Simply put, loadings are interpreted as the coefficients of the linear combination of the initial variables from which the principal components are constructed. So remember, principal component is nothing but a linear combination of the original predictor variables. So if they are a linear combination, then obviously there will be coefficients by which that linear combination is formed. Hence those coefficients are called as loadings. The higher the loading, the higher is the correlation of that variable with the respective principal component. It basically gives us information about the important variables or contribution of the variable for constructing a particular principal component. Now loadings are the elements of eigenvectors, and it will always lie between -1 to +1. Eigenvalues are the diagonal of variance-covariance matrix of principal components, and it is equal to the variance explained by PC. Then we have scores. Scores are the representation of feature X, that is the predictor, in the principal component space. So scores vector is equal to X, the matrix of predictors, multiplied by loading vector. Let's understand it through an example. Let's assume below is our data. And let's just assume that this is scaled. Now after performing PCA, we get our PCs as below. Each element of PC is a loading. We can calculate our new data in the rotated space or in the principal component space by simply multiplying loadings to the predictors. So what is happening here is each predictor is now becoming a linear combination of all the predictors. Now the values in the above table are called loadings, and the new data in the rotated space is our scores. So that is how we calculate loadings and scores. So this was principal component analysis in a nutshell. Now let's quickly revise what we have covered so far. In this video we had discussed about PCA, then what are the goals of dimension reduction, then what are the steps involved in PCA, and then what are loadings and scores. Alright, so let's do an assignment in R now. So I'll see you in the next video then.